Okay, so we saw two extreme modulation schemes, one using really high frequency, the other one using a fundamental frequency of switching. As we discussed, that fundamental frequency of switching creates a problem because then you have lower harmonics as low as third and fifth, which might be really difficult to filter out, and you might require a really large filter. So what we are going to see now is something called as a selective harmonic elimination method, right? This selective harmonic elimination method does something in between. So it maintains switching frequency between very high and fundamental, as well as it eliminates some of the lower order harmonics like third, fifth, and so on. So let us see that method, which is called as selective harmonic elimination method. It's also abbreviated popularly as SHEM, right? Selective harmonic elimination method. So although we have already seen this circuit, which is a full bridge converter, or rather a edge bridge inverter, what we will do is, just to understand this method, we would try to use another circuit. You can very well apply this method onto this circuit, but I wanted to introduce you to the other circuit, and therefore I would just introduce you to the other circuit and then try to apply this method so that you become familiar with the other circuit also. So this is also an inverter. This is called as a half bridge. The left one is full bridge, right one is half bridge converter. If you see, there's one wire which goes from here and the other wire which goes from here, right? So this is switch S1, switch S2, and this is VDC by 2 and VDC by 2. So instead of using 4 switches, this uses only 2 switches. And because you have only 2 switches, so there are only 2 states here. One state is when S1 is on and S2 is off. In that case, your V1 is nothing but equal to VDC by 2, and the other state is when S2 is on and S1 is off. In that case, it is minus VDC by 2. So in this half bridge converter, you would have realized one thing is that yes, you can work with just 2 switches, but then the problem is that you do not have any zero state. You only have active states. And because of that, you cannot use unipolar modulation. You have to use bipolar modulation, right? So your waveform for V1 will always going to be bipolar in nature. It would not be unipolar. It will have a fundamental component, but the waveform V1 would be bipolar in nature, and therefore you may not really want to use half bridge converter, right? And therefore a lot of times people use full bridge. If you don't want to use so many switches, you can use half bridge also. Now let us see how to apply, what is this SHEM and how to apply in this case. Before moving ahead, let's say if this would have been a fundamental modulation, then how do we do? If this would have been a fundamental modulation with this bridge, let me redraw the bridge anyways now from here. S1, S2, and this is V1. Now if you are doing fundamental modulation, which we just saw, then here you cannot have a zero state, so you would have only plus state and you will have only minus state, right? So if you do fundamental modulation here, then you are kind of stuck with the RMS value, because if you shift this point not to T by 2, if you shift this point either to left or to right, then you will have DC offset, which you don't want, right? You don't want any DC offset in the AC signal, and therefore in this circuit you cannot really manipulate the RMS value using fundamental modulation, right? Because you don't have zero state. So next thing, what will you do? Okay, maybe you would add some more switching, for example, and you would try to create this kind of waveform. So in this case, let's say I'm adding one switching here, then another switching here, and third switching here, right? And I've only drawn it till t by 4, so these are not time aligned. This is only t by 4, or rather 90 degrees. And you want symmetry, so therefore this waveform would continue. So let's say here we have I can just try to draw it. So this waveform, we would want quarter wave symmetry so that we do not have any even harmonics, and therefore we would draw it like this, and then it would, on the negative side also, it would have the same waveform. And so on, right? So this is 3t by 4. This point here is t by 2. So this waveform, we would like to have quarter wave symmetry, and that would ensure there is no even harmonics, right? So if you see this waveform, let me draw the above waveform also in the same time axis, so it's easier to sort of. So if you see this waveform, we are obviously switching a little bit more. How many times we are switching? First one in the first period, if you see S2 is on, right, then S1 is on, then S2 is on, then S1 is on. So I go from S2 to S1, then S2 turns off, then again it turns on, and then again it turns off, right? So S2 is, and I can continue, this is also S1, this is again S2, this is S1, S2, S1, S2, and so on, right? So if I see starting from this point, I'm going from S2 to on to off, then again on, so it completes one switching cycle for S2, then again off, right? So almost 1.5 switching cycles of S2. And if you see S1, it is going from off to on, and then again off one cycle, and then again it turns on. So again 1.5 switching cycles for S2 is what is happening in this quarter cycle, right? Similarly, you can count for remaining parts also if you want, or you can use symmetry and directly express that. So yes, we are not switching, we have gone more than a fundamental, right? Maybe roughly around we have gone about 5 to 6 times the fundamental, probably, right? 6 times. So we are switching 6 times each switch in full 50 hertz. Earlier we were switching only once. But now what have we gained? So let's say these instant of switching, let me define it as alpha 1, alpha 2, and alpha 3. Right? The other angles you can write in terms of 1 to alpha 1, 2, and 3. So what we have gained is we have the control, we can manipulate this alpha 1, alpha 2, and alpha 3 values to get some gain out of it. What is the gain? The gain is in terms of lower order harmonics. If you see, if I write the Fourier expansion of this particular, or Fourier, I write in terms of Fourier series this particular waveform, then I can write it as A0 by 2 plus sigma an cos of nx, n going from 1 to infinity, plus sigma bn sine of nx, n going from 1 to infinity. Right? If you see this waveform now, wherein A0 is given by 1 upon pi integral minus pi to pi fx dx, an is given by 1 upon pi integral minus pi to pi f of x cos of nx dx, and bn is given by 1 upon pi integral minus pi to pi f of x sine of nx dx. Because of quarter wave symmetry, an will be 0 and a0 will be 0, right? Both a0 will be 0, an will be 0. You can try to feed this fx from here and you can see it yourself. And also bn is equal to 0 for n even. For n even, bn is also equal to 0, and that means b2 will be 0, b4 will be 0, and so on. So only thing that is non-zero is, let's say, bn where n is odd. For example, let's say b3, right? So what is, let's try to find, for example, b3 or maybe b1 also. Let me call it just bi. So bi is 1 upon pi integral, because of symmetry you can write 0 to pi by 4, 0 to pi by 2, f of x sine of ix into dx, right? You can further write it as 1 upon pi integral 0 to pi by 2. Okay, so instead of directly going 0 to pi, let's go from 0 to alpha 1. Fx is minus vdc by 2, right? Sine of ix dx plus integral going from alpha 1 to alpha 2 vdc by 2 sine of ix dx, and similarly going from alpha 2 to alpha 3 there will be one more integral, plus there will be one more integral going from alpha 3 to pi by 2. So you'll have total 4 integrals, right? You can solve for these 4 integrals. These sine would get converted to cosines, right? And you can do a little bit of rearrangement and you would be able to get this equation. Cos of I alpha 1 minus cos of I alpha 2 plus cos of I alpha 3 is equal to I times pi times b of I plus 2 times VDC upon 4 VDC. Right? This is the equation that you would get. If you see how many unknowns are there, there are alpha 1, alpha 2, alpha 3 are unknown. Right? I can write this equation for fundamental component for I equal to 0. I can write this equation. I can write this equation for I equal to, for I equal to 1 I can write, for I equal to 3 I can write, for I equal to 5 I can write. I can still write it for I equal to 7, but then I will have 4 equations and 3 unknowns. So then I may not be able to find a solution. And therefore, since there are 3 unknowns, I restrict myself to 3 equations. I feed alpha I equal to 1, right? And I will, on the right hand side, if you see bi also is something which you can feed. So let's say I equal to 1. Now bi is nothing but the magnitude or the peak value of the fundamental component, and therefore let's say bi is what you have selected, right? What you want to have the fundamental component. For example, if you see this Fourier coefficient, where is bi? Yeah, so this is bi. So if I is 1, this is sine theta. So this is nothing but the fundamental component, peak value. So so bi you can select, right? And similarly I3, that means b3 you would want ideally to be 0. You don't want any third harmonic. And similarly b5 also you want it to be 0. So if you use these 3 conditions, you will get 3 equations, right? And you have 3 unknowns, alpha 1, alpha 2, alpha 3. You solve them and you get alpha 1, alpha 2 and alpha 3. And this is the alpha you set in your inverter, and then you will get a waveform looking like this, which will have the desired fundamental value which you have set, and here I have 0, 3rd and 5th harmonic. So you see you are able to eliminate only 3rd and 5th very precisely, right? And thereby increasing your cutoff frequency of filter, because the next harmonic you will have after 7th is now 9th. So that is how this selective harmonic elimination method helps. If you want to eliminate 9th, that means you want one more equation. That means you have to add one more switching. You add one more switching, right? So as the more the number of harmonics you want to eliminate, the more the number of variables you would have to add to achieve that. So so you can theoretically do it even for very high frequencies, but then the problem is, because these equations are nonlinear equations, these equations corresponding to different values of I, they are nonlinear equations, and therefore it becomes difficult to solve them online. So you cannot solve these, you cannot solve these nonlinear equation very easily, and that is the reason you don't really, I mean, solving even 3-4 equations is challenging simultaneously. Then if you can imagine, if you have 10, 20, 30 equations, it will become even more challenging. That is the reason people don't use this method for really high frequency applications. For even with 3 or 4 equations also, a lot of time people would solve these equations offline for different values of bi, right, and store in the memory of a microprocessor, and then based on the bi value that you want to actually realize, you pick up those values of alpha 1, alpha 2 and alpha 3 from microprocessor or memory, and you implement that. Right, again you can so you can control the magnitude. Phase angle you can anyways control by providing a phase shift to the complete switching cycle, right? So you can control both the things, plus you can eliminate third and fifth, or even ninth or even 11th, depending on how many number of switchings you incorporate. This method we have discussed for half bridge. You can very well apply it to full bridge also, right? You can try to do it yourself. There unipolar kind of modulation is possible, so you can have a unipolar trend, you can still define different values of angle alpha and then try to solve it.